All right, so welcome back. I hope you're well entertained by Dr. Pham and Dr. Kovner. I know Dr. Kovner didn't finish Heisenberg uncertainty principle and the diffraction spectroscopy. So what I'm going to do is I already uploaded the new version of lecture 6, so you can go ahead and listen to my recording. I'm also going to go over those two topics in the buffer lecture before midterm 1. So I'm not going to put these two topics on midterm 1. You might expect it on the final though. So just this is what I want to do to make up for the progress. But you should have all the equipment you need for us to discuss the Schrödinger equation today. So we'll finally get into the Schrödinger equation, which is at the heart of quantum mechanics. So today we'll be talking a little bit of the Schrödinger equation. You can't really derive Schrödinger equation, but I can try my best to help you understand what's the physical meaning of Schrödinger equation. And we're going to look at one simple example and see how can you solve the Schrödinger equation for the most simplistic example here, which is the one-dimensional particle in a box. Okay. So before I get started, I'm also aware we're having the discussion worksheet arranged not the ideal way. Say last week's discussion, you will need a Bohr model to finish. I try my best to reorganize the discussion worksheet. So this week's discussion worksheet only goes to today's lecture. You don't need the Friday lecture to finish the discussion worksheet. So eventually, I hope you only need the Monday lecture to finish the discussion worksheet. So I'm working on it. I hope it's on the right track right now. Okay, do we have any administrative question before we start? Okay, right. So let's get started with the Schrödinger equation. So first thing first, what is Schrödinger equation? So Schrödinger equation gives you the Schrödinger's wave function phi that characterizes a wave that's associated with a particle at position x, y, z, and time t. So if we write out the actual Schrödinger equation, what we have here is first we have the Hamiltonian operator. You don't need to know what that means. And wave function phi as a function of x. Well, let me use a different color here. X, y, z, which is position, and time t. The Schrödinger equation is a differential equation. We'll see why that's a differential equation soon. That gives you the energy times x, y, z, and t. All right, so phi, the wave function itself, is a function of position and time of a specific particle. So let me write down what we have here. So this Hamiltonian, that's an operator that tells you about energy, and you don't need to. And then phi here, that's a wave function. And the solution will give you energy that is quantized. So again, we can't really derive Schrödinger equation like what we did with the Bohr model, but I'm going to go over some of the things that's behind this simplistic version of the Schrödinger equation and see if you can get more physical insight into it. Okay, so if you have a piece of paper or a blank note, we can work on this together. Again, like what we did with the Bohr model, you did with Dr. Pham with the Bohr model, we always start from the representation of energy. So my equation 1 is just tell me energy, total energy, equals to kinetic energy plus potential energy. That's not helpful, sorry. And then the next step, what we do is we multiply both ends with the wave function phi x. We're not talking about what phi x mean, but let's just bear with me a little bit and see how it works out. For simplicity, I'm just going to talk about the one-dimensional time-independent phi x. So instead of phi x, y, z, and t, let's just focus on one-dimensional problem. So E phi x equals to kinetic times phi x plus potential times phi x. All right, nothing fancy. We're just multiplying both ends of the equation with the wave function phi x. And next up, let's write out the kinetic term, this one here. What we have is we know kinetic energy equals to 1/2 mv squared. Or we can also write that v into linear momentum. So this is to linear momentum. We know P equals to mv, that's linear momentum. So we can rewrite kinetic energy into 1/2 m times P squared m squared. That equals to 1/2 P squared over m. So far what we're doing is still like the classical definition of kinetic energy and try to understand what's the meaning here. And combine this equation, which is kinetic energy equals to 1/2 m P squared over m squared, and rewrite that energy expression. What we have is, use a different color. Energy times phi x equals to 1/2 P squared m phi x plus potential energy times phi x. So again, what we're doing here is just rewrite that kinetic term, right? 1/2 mv squared into an expression of linear momentum. With me so far? Okay, and now let's try to introduce the quantum part and see how they connect. We talked about the de Broglie, Dr. Kovner talked about the de Broglie wavelength last lecture. So we have lambda, the de Broglie wavelength, equals to h over p, which gives you p equals to h over lambda. So this is my equation 5, just at the de Broglie wavelengths. And our next step is a little bit weird if you're not familiar with differential equation or the physics behind it, but I'll try my best. So this next step, you don't really need to understand, you don't really need to know the mathematics behind it. So what we're doing for our next step is square it and then multiply it by phi x, right? So our equation 5 is P equals to h over lambda. So what we're doing is just multiply the wave function on both ends and square it. And then this part is slightly weird, so just accept it for now. What it says is for a general wave, which in this case our phi x is a wave function, right? It is a wave. So for a general wave, which lambda is not well defined. So in this case, our wave function has a lambda that is not well defined. The action of p squared, the linear momentum square, is equivalent to a second derivative. Right, it is a little bit odd, and if you don't have the math behind it, just accept it as a fact that the p squared times phi x is roughly given by this negative h over 2 pi squared and the second derivative of phi x. And this goes a little bit back to our differential equation background. Remember, when we're talking about the derivative, we're talking about the rate, the change, or the slope. right? The second derivative is the slope of a slope, if you may, or it tells you how fast your wave gonna oscillate. So again, I'm gonna try a little bit harder and see if you can get a qualitative understanding. So imagine you have a wave function that oscillates fast. It has high frequency, it has a small wavelength, and also consequently a large linear momentum because p equals to h over lambda. And the second derivative describes the rate of change. So if it's oscillating faster, it is expected to have a larger rate of change. So I'm trying to make a qualitative comparison between the linear momentum and second derivative. But if it doesn't click to you, it's also okay. Just accept it, saying the linear momentum squared acting on the wave function is equivalent to, say, the second derivative acting on the wave function, which I don't know what happened. Okay. All right. So this is a little little thing that I hope you could get. And now we're combining the equation 4 and equation 6. I'm just going to write it down for you for your reference. Equation 4 gives you energy times wave function equals to 1/2 p squared over m times wave function plus potential energy times wave function. And then equation 6 gives you p squared phi x equals to negative h over 2 pi squared d squared over dx squared phi x. And again, just one of the common mistakes if you're not familiar with calculus, you cannot cancel out these two terms because this one is a second derivative, right? This is a differential equation. You cannot just cancel it out. That's not a reasonable thing to do. All right, so taking these two equations together, we get a new equation, right? We're just plugging this p squared phi x into there. And our new expression gives E phi x equals to 2m over 1 times this negative h over 2 pi squared d squared dx squared phi x plus potential energy phi x. Or let's cancel out some of the terms and simplify it. And we have E phi x equals to negative h squared 8 pi squared m d squared dx squared phi x plus potential term ux phi x. All right, so this is our one-dimensional time-independent Schrödinger equation. So this is how we get to that abstract form, to this more well-defined equation, if you may. So this first part, this is our kinetic energy. And the second part, that's our potential energy. All right, so that's our one-dimensional time-independent Schrödinger equation. It's the same idea, right? Remember when we write it as the Hamiltonian phi x, E phi x. Sometimes people can also rewrite it as the kinetic Hamiltonian phi x, plus potential Hamiltonian phi x. That gives you E phi x. So if we compare these two, what we have is this kinetic Hamiltonian is more or less just that second differential equation we're talking about. I did not show you the full picture of that potential energy. It can be a Coulomb's potential. It can be any kind of potential you like. But we'll give you a clear definition if that's ever applicable. All right, so here is just a quick demonstration on how do you actually get from the relatively abstract form of the Schrödinger equation to the more well-defined differential equation we're talking about. So the nature of the Schrödinger equation, it is a differential equation. Okay, I know it is still confusing, so I'm going to spend a little bit of time just talking about the physical meaning of the Schrödinger equation. Let's leave all the math behind. Just think about it, really think about it, what it means when we have the Schrödinger equation. So, again, we're going to use the one-dimensional time-independent Schrödinger equation as an example. We write it down here. It's Hamiltonian acting on the wave function gives you energy times the wave function. Right, so this little thing is Hamiltonian operator. And what we just see is the Hamiltonian operator is more or less a differential equation, at least for the kinetic part. I just showed you what the one-dimensional time-independent Schrödinger equation looks like. That's negative h squared over 8 pi squared m d squared over dx squared acting on phi x. All right, so this is my Hamiltonian kinetic plus ux phi x. Imagine this is my Hamiltonian potential. And gives you energy phi x. A little bit of the extra, if you're already taking linear algebra, eventually you'll see these differential equations, or my Hamiltonian, it is actually a matrix. And by solving that matrix, the energy you're getting is the eigenvalue of that Hamiltonian matrix. But that's just an extra. I'm not going to test you all that. So the nature of the Schrödinger equation is a differential equation. And what we're getting out of the Schrödinger equation. So here's what we're getting. By solving the Schrödinger equation, you're going to get a wave function phi x. And phi x can tell you everything about the particle of interest. So I always like you to think about it like this. The wave function is like an oracle that knows everything. But the problem here is, in order for the wave function to tell you that's everything, in order the oracle to tell you the correct answer, you need to have the correct question to ask. All right, so what happened is you use the correct question. That question here is a operator. Whether it's Hamiltonian, if you use Hamiltonian as a question, the wave function gives you energy. Or if you use other operator like a momentum operator, the wave function is going to tell you what the momentum is. All right? The other way to use the wave function, which is something that we will discuss a lot, is a probability. So this phi x wave function squared, absolute value squared, that gives you the probability density function. So our wave function, it is not a light wave or a plane wave, if you may. It is more or less a probability wave. So the wave function squared, by definition, gives you the probability density function. And because it is a probability, now we have boundary conditions that gives the wave function physical meaning out of it. So the boundary conditions coming out of it is that if you do an integral from negative infinity to infinity, means we go all the way span of this probability density function, it will add up to be 1. So remember, we use the wave function to define a particle, right? So the wave function is a probability wave. If we're taking the probability density, which is the wave function squared, you take the integral over all space, you're guaranteed to have the particle somewhere in space. So this boundary condition is giving my wave function a physical meaning. Okay? Yes?
So this is the probability that a particle is in a given space?
Yes. So for example, I'm saying that's a boundary condition, right? So if you take the integral for all space, it must add up to be 1. But imagine if you're just taking the integral in a given space, you get the probability of finding that particle in that smaller given space. We'll see more examples soon. And just again, as a quick extra, in order for this integral to converge, we have 2 more boundary conditions. That's like when phi x approaches 0. Well, when x approaches infinity, phi x will approach 0. And also the other requirement is that phi x squared must be a continuous function. And these are just extra, like if you're taking calculus, you'll see why they're the case, but if not, it's okay. Right, so follow up to the question. One of the applications of using the wave function is, say, imagine you have phi x. Now it is a one-dimensional wave function of some random particle, delta. And you write an integral to solve for the probability of finding this particle somewhere between 4 to 6. So writing that integral, so knowing what the wave function means and knowing what that probability density means, you can write that integral out. You don't need to solve it, but at least you need to know. You should write it like 4 to 6. And we have the absolute value of phi x squared dx. So this is the integral that gives you the probability of finding this particle between 4 to 6. All right, that's the one way of using the wave function. The other way to use the wave function is, like I said, it's an oracle. So you can get any physical property about the particle as long as you have the appropriate operator for it. So for example, for energy, we use a Hamiltonian operator acting on phi x. That gives you the energy times phi x. You can also get the angular momentum if we're using the angular momentum operator. And that gives you L phi x. Likewise, if you want spin, use the spin operator. So one of the example questions could be, imagine a random physical property like linear momentum, right? If I tell you the linear momentum operator and the wave function then you should be able to set up these equations and say, hey, we're just going to apply the linear momentum operator on the wave function to get the linear momentum out of it. It might have some simple math associated with it, but nothing that's complicated. If we're using calculus, I'll give you what those derivatives are. Okay. So before we move on to the one-dimensional particle in a box, I want to stop here for a nice solid 5 minutes and see if we have questions. Or if you want, yes?
What do you mean by using the different operators? How does that apply to the Schrödinger equation? I don't understand how that works.
So what happened is solving the Schrödinger equation gives you the Schrödinger wave function. So that is the phi x here. And by knowing the wave function, now if you have the appropriate operator, use the operator to act on the solved wave function. It will give you the answer, which is the physical property you're asking for. All right, so that's the connection here. It's solving the Schrödinger equation, you get a wave function. In order to use the wave function to get physical property like position, momentum, speed, you're going to use the appropriate operator for that to extract information from the wave function. All right, yes?
So the wave function, you mentioned that as the limit of x and the wave function approaches infinity, the wave function approaches 0. Is that true for both positive x and negative x?
Right, so the question here is, does this boundary condition apply? So yes, that's true. I mean, for both positive infinity and negative infinity, your wave function needs to apply to 0 in order to have that probability integration converge.
So I guess more what my question is where would the values in this equation be clustered? Like, is it like some kind of...
So try not to think about any specific value when you're thinking about the wave function. We're going to see an example in the one-dimensional particle in a box. I hope that's going to help you a little bit. It's not any specific value we're talking about. It's just imagine that as an abstract wave function. As long as it's continuous, it's approaching -0 when x is approaching infinity, that can serve as a potential wave function. So right now, try not to think about it as any specific wave. Okay, so let's look at the one-dimensional particle in a box as an example, and I hope at the end you'll see more like what does it mean when we're talking about Schrödinger equation. All right, so I'm going to put my setup here on the side projectors. So when we're working on it, you should be able to go back to see the physical setup. Let's see, is it big enough? Okay, is it big enough for everybody on the back to see it? Okay, sounds good. So I'm going to walk you through on the setup of the one-dimensional particle in a box for now. What we have is, it's a one-dimensional problem. The only variable is position x. So now imagine there's a little bead that's sliding along a line. It's not really sliding, but the particle is confined in that one-dimensional line. That's between two solid walls. All right, so here are the two solid walls. The probability of finding the particle outside the box is 0. So I'm just going to spend some time here. So when we're talking about the probability of here, is these walls have infinity potential. All right, so what that means is it's just a solid wall. Your particle can never go beyond those infinity potential walls. Actually, let me just zoom it out. This is more helpful. Okay. So the probability of finding the particle outside the box is just going to be 0. Or the other way to put it is phi x equals to 0. For x smaller or equal to 0, and x larger than or equal to L. So again, what we're saying here is just translating those infinity walls into wave function. So there's no probability of finding the particle outside the box anywhere in space. The other thing it gives you is the potential inside the box is going to be 0. So my potential term, Vx or Ux, is going to be 0 for x within the box. Let me just write it down here. So phi x equals 0 for x smaller or equal to 0 and x larger than or equal to L. And then inside the box, the potential term is 0. So these are the terms we already know. Is it showing up?
Is potential energy 0 because it's continuously moving?
No, we just define it to be 0.
Oh, okay.
Just to make our life simpler. You can add potential energy in there as well. So now let's do the derivation and try to actually solve for a wave function in real life, right? So this is as simple as you can get. Inside the box, there's kinetic energy. There's no potential energy. Outside the box, there's wave function just equals to 0. So it's one-dimensional. So use a one-dimensional time-independent Schrödinger equation. Outside the box, there's no wave, so we don't care about whatever happened outside the box. We're just looking at inside box. And we have Ux equals to 0. All right, so inside the box, we can simplify this one-dimensional Schrödinger equation into energy times phi x equals to negative h squared 8 pi squared m d squared dx squared phi x. So Ux equals to 0. So this term goes to 0. So I don't need to show the potential term. So that's our differential equation we have. And now let's rewrite that equation 8 a little bit to make sure that's a differential equation. So d squared over the x squared phi x. So that's this part. I'm just rewrite it so it's on one side of the equation. Equals to negative 8 pi squared m times e over h squared phi x. All right, so what I'm doing here is just rewrite equation 8 so that the second derivative is on one side of the equation. And here we're going to use a little bit of calculus because this is a differential equation. This is the second derivative of some mathematical function. On the right-hand side, we have that equation itself. So I'm going to use some magic calculus here. It's that whenever so we want an equation whose second derivative is itself. So in calculus, we have 3 candidates at least. It can be a cosine x function, a sine x function, or an exponential function, right? So in this case, the calculus we're using is what equation. We want an equation whose second derivative is the equation itself. So this one is simple. It's just like you're going to choose between these 3. And the way we choose between these 3 is using the boundary condition. So we have some boundary condition here, right? Remember what we have is phi x equals to 0 whenever x equals to 0. So that's one important boundary condition we're going to use. I'm also rewrite it here. So what does this function look like? The cosine x at 0 that's like this, right? So that's my cosine x. That doesn't work. It doesn't equals to 0 when x equals to 0. The exponential one doesn't work because when x equals to 0, ex equals to 1, so that doesn't work. So the obvious choice here is a sine function. So phi x equals to, I'm going to just write a general form of the sine function, and we can solve for those parameters later on. So a sine kx. All right, so this is just a general representation. All right, so the way we get here is by just think about differential equation. What we want a function whose second derivative is itself. And then we have 3 candidates. By looking at the boundary condition, we think the sine function works the best with my boundary condition. And that's how I rule out cosine and exponential function. They will come to play in other setup, but not in the one-dimensional particular box I'm showing right now. Okay. So now we have 2 different terms we need to solve. One is this A coefficient. That's what we call the normalization coefficient. We'll worry about it later. And now let's just look at this K. How can we solve for the K with the boundary condition we're getting? So again, we're using the boundary condition. So we know that phi x equals to 0 when x equals to 0 and x equals to L. All right, so that's given in this box. We know that phi x equals to 0 when x equals to 0 and x equals to L. So far, we use that x equals to 0 term to rule it out to the sine function. Now we're going to use the phi x equals to 0 when x equals to L. We're going to use that to solve for our coefficient k. What it means is that when x equals to L, and remember we have phi x equals to a sine kx. So what we're doing is just plugging that x equals to L here. We have phi L, or x equals to L, equals to a sine k times L, and this always equals to 0. All right, what we're plugging in is just plugging this x equals L term into that generalized sine function. And we can look at what the sine function is if you're not so familiar here. We have the phi x equals to 0 when x equals 0. It also equals 0 when you add pi, 2 pi, 3 pi, etc. So what that means is my KL. So if my KL equals to, if my KL equals to n pi, where n equals to 1, 2, 3, etc., my sine n pi always equals to 0. So this comes from looking at the sine function. Right? We know that sine n pi equals to 0. So that's how we get the equation KL equals to n pi. So solve for K. What we have is K equals to n pi over L, where n equals to 1, 2, 3, etc., as long as it's integer number. Right, so nothing fancy here. We're just looking at the sine function and try to find out where does my sine function equals to 0. And what we identified is my sine function equals to 0 whenever you have n pi, whenever that sine n pi always equals to 0. So from there, we deduct that my k equals to n pi divided by L. All right? So plugging that k we now have phi x equals to a sine n pi L, remember my k equals to n pi over L, times x, where n equals to 1, 2, 3, etc. So what we're doing here is just plugging that k. All right, so we're halfway through. We get what k equals to in my wave function. With me so far? Okay. And then we need to use integration to solve for that normalization function, normalization coefficient A. So remember, we're talking about a probability function. A wave function is a probability wave. The absolute value squared gives you the probability density function. Again, what the probability density function requires is that if we take the integration for everything, every space inside this box of 0 to L, and this is my wave function, right? So this part is my wave function. This is what we have solved for. This is our phi x, absolute value squared. So take that wave function squared, integral it through the entire box. The probability must add up to 1. So this is what we have. And this needs some calculus, so I'm just going to solve it for you. So by solving that integration, you're going to get A equals to 2 over L. All right, so 2 steps. The first step is we use the boundary condition to identify that sine function is the most appropriate function to use. And then we use the boundary condition to solve for k and to solve for the normalization factor A. So taking together, we now have the wave function phi x for one-dimensional particle in a box. So that 2 over L, that's my normalization coefficient, times sine n pi x over L, where n equals to 1, 2, 3, etc. All right. How are we feeling? Okay, so now we have the wave function. We have a real mathematical function that describes the one-dimensional particle in a box. Remember the one-dimensional particle in a box? Imagine you have this particle inside this one-dimensional box. It might be anywhere in the box, but now we have a wave function to describe that particle in that one-dimensional box. And now let's look at how are we going to use the one-dimensional wave function to get physical meaning, to get things we care about of this particle. So how do we use it? 2 major things, right? One is use the correct operator to get physical properties out of it. So let's just first solve for the allowed energy values. So this is the wave function. This is the Schrödinger equation we had before. And we have the wave function that we solved. So let me just copy paste that down. And what we want to do is to solve the second derivative of phi x. And now just given the second derivative of the sine function is negative n pi over L squared times the sine function. So we can solve for it. E phi x equals to negative h squared 8 pi squared m, and then we have the differential term, which equals to negative n squared pi squared L squared. So this part comes from your magic calculus, phi x. So this phi x, although it is, these two are equivalent, I mean, I just didn't bother to write it all up. All right. I want to cover it up. And then here we can cancel out some of the terms. Now it's no longer a differential equation, so that's why I can cancel out my phi x. We don't have any differential equation in here, and now I can cancel it, just the sine function. And we have the energy expression. On the left-hand side, that's just the energy. We don't have a negative anymore. That's good. We don't really want the negative to be around. We have n squared, h squared, so the negative canceled out, pi squared canceled out. On the bottom, we have 8m L squared. N equals to 1, 2, 3, etc. All right, so this is how you start from just the physical definition of a problem, the one-dimensional particle in a box problem. What we did, we solved its wave function by just looking at its boundary condition, by just using the Schrödinger equation. It's solving the differential equation. You end up with that sine function, which is a wave function describing the one-dimensional particle in a box. And from the wave function, we can solve for the quantized energy levels for a particle in a one-dimensional box with length L. All right, so that's a quantized energy level of that particle in the box. The other way to use the solved wave function is to solve for its probability. We already see it before, so the same idea is, say, I want you to set up the probability integration, right? So the probability of finding the particle between x1 and x2, assuming that's within the box. We have p x1 to x2. It's given by this integral. And in there, we have the phi x squared, which is 2 over L, sine squared, n pi x over L dx. So in your discussion worksheet, you need to probably just actually need to do that integration to get an idea about what that probability looks like. But I hope today is, it's a little bit abstract, but it's just to give you a pretty high up look on what the Schrödinger equation is. So far we've finished everything about the foundations of quantum mechanics. So you can tell your friend you know quantum mechanics now. We start from the very basic quantum hypothesis, black body radiation, wave-particle duality. Dr. Fan went you through with the atomic spectroscopy. Dr. Kovner told you about the Broglie wave. We'll work on uncertainty principle later. But today we finished the Schrödinger equation. All right, so we are finished with the foundation of quantum mechanics. I have office hour at the Young Hall 3077 from 10 to noon today. So if you want to stop by, we can also discuss more. All right, thank you.